Welcome. This video is going to continue to look at the relationship between the electromagnetic spectrum and how it helped chemists understand atoms. So the light and all the waves on the electromagnetic spectrum were thought to contain energy only and to travel as waves, which is what physics studies. But just waves of energy, or this wave theory, can't explain how or why heated objects emit only certain colors of light, or why some metals emit electrons when light shines upon them. So Planck and other scientists tried to come up with some answers and a new model. So Planck's work found that heated metals emit specific colors or frequencies of light, and as objects get hotter and possess more energy, the color of that light or the frequency of that light changes. For example, in this picture here, these are all pieces of iron here with similar shapes, and the unheated or room temperature iron is gray, like you're used to seeing, or kind of silvery. And as you heat it up, it first glows red, and if you get it really hot, then it glows orange. So Planck wanted to figure out what is going on, what's emitting the different colors. And he found that matter can only gain or lose energy in small, specific amounts, kind of like going up a ladder one step at a time instead of walking up a ramp. You either go up a full step or you don't. There's not an in-between amount. But on a ramp, you can make your steps as infinitesimally small as you want. You can just barely creep a millimeter forward. But when you're on a ladder or a staircase, you either commit to a step or you stay on the step you're at. And Planck found that that's true with atoms, that they gain or lose energy in these small specific amounts or steps. And he called those amounts a quantum. So a quantum is defined as the minimum amount of energy that can be gained or lost by an atom at a time. And so the equation or relationship he came up with frequency and energy, so the light that we see emitted, is that if you take a constant, which he happened to name Planck's constant, this constant times the frequency will always be equal to the amount of energy that's being released. Or the energy will be equal to Planck's constant times the frequency. And Planck's constant is a very small number, as you can see, 10 to the minus 34th. And the unit given is joules per second, because that means the energy then is measured in joules, and the frequency is measured in per seconds or hertz. And you might notice I have the energy of a quantum equals Planck's constant times frequency, and the energy of a photon also equals the same amount. And we're going to talk about photons a little bit later, but just to preview for you, quantums and photons are very similar, and in fact their energy is the same. It's interchangeable. So let's take a look at a couple examples. It says calculate the energy of a gamma ray photon whose frequency is 5.02 times 10 to the 20th hertz. And my hint to you is that you have two equations to choose from. So look at what you've been given and what you must find. And so if you want to try this on your own, this would be a good time to pause it. Otherwise, I'm going to go ahead and advance to the next slide and work my solution. So I've been given frequency right here, 5.02 times 10 to the 20th hertz, and I've been asked to find energy for this frequency. So the equation that best suits this is E equals h times v. So E is what I'm trying to find. H is a constant. It's 6.626 times 10 to the minus 24th. Remember that unit's joules, seconds. And then if I plug in the frequency as given, that is 5.02 times 10 to the 20th. And remember, a hertz is just a per second. So that means my seconds are going to cancel, and whatever this value is, my energy should be expressed as joules. So if I go ahead and plug this in, I'm coming up with an energy equal to, I guess I don't need two equal signs there, but I'm coming up with energy equal to 3.33 times 10 to the minus 13th joules. So that's pretty straightforward when you're using frequency to determine energy. So let's look at another example here. It says calculate the energy of a photon of ultraviolet light that has a wavelength of 49 nanometers And again, remember you have two equations to choose from, so look at what you've been given and what you must find. And also pay attention to your units because this is nanometers. And just like with E equals wavelength times frequency, you have to make sure your units match when you have a constant in there. These nanometers are going to have to be changed to meters. So if you want to try this on your own, this is a good place to pause. Otherwise, I'm going to go ahead and advance the slide and work my solution. So again, you've been given wavelength and asked to find frequency, but I do need my wavelength in meters, so my starting point is going to be to take that 49 nanometers. I want meters, I have nanometers, and what I know about meters and nanometers is there's only 10 to the minus 9th meters in 1 nanometer, or it's a meter cut into a billion pieces. So this is really 49.0 times 10 to the minus 9th meters. And now when I plug in, my equation gets a little messier because I have 6.626 times 10 to the minus 14 or minus 34 joule seconds for H. I have 3.00 times 10 to the 8th meters per second. And finally I have 49 times 10 to the minus 9th meters. And if I look at all those units, the meters cancel, the seconds cancel, and when I plug this in and come up with my final value, this value will be in joules again. And I'm coming up with 4.06 times 10 to the minus 18th joules. And again, small amounts, but not a big surprise given how small Planck's constant is. And remember, we're talking about energy being gained and released in a single atom. So these are going to be extremely small amounts.